Hi guys, we're on rational function graphing examples day 2. So on this example, let's remember that on rational functions we always want to factor if we can first. So we're going to factor the top to x minus 2, x plus 2. This is over x plus 2. And then we can see that we can actually simplify this rational, right, by canceling the common factors. And so what I have left is y equals x minus 2. This looks like a linear function, right? So this is what I have left. That means what I am graphing is now going to be linear. It started off as a rational though, right? So we also have to consider our excluded values. Remember, that's when the bottom is equal to 0. So if I set my bottom equal to 0, that means x would be 0 when would be negative 2. That would make x 0. So we can't have that happening. Put that together with the fact that I have a line. So remember, lines are continuous, but I can't be continuous when x is negative 2. So what's going to happen is we're going to have what's called a removable discontinuity at x equals negative 2. Otherwise, you can call it a hole for a more friendly term. So to figure out where exactly this hole is, I know it's happening at negative 2, but I don't know the y part of that coordinate. So what we're going to do is we're going to substitute it into the line equation. Negative 2 minus 2 gives back negative 4. So that means this is where my removable discontinuity is happening, at negative 2, negative 4. So what we're going to do is draw an open circle. Remember from earlier this year that shows that it's discontinuous at this particular point. Okay, other than that, you're going to graph your line like you normally do with your y-intercept, and you're going to apply your slope, right? You're going to connect the dots that we've got here. Make sure that you're not going through your removable discontinuity. All right, so now we're moving on to example 2. And again, what we're going to do first is check to see if we can factor anything on our rational function. And the top does factor to x minus 3 and x plus 3 all over x minus 3. And then we can see that they do have a common factor that does cancel. And again, that leaves us with something that looks like a linear equation. So again, we're going to be graphing a line, but we do still have to worry about our excluded value here. This is when the denominator is equal to 0, and that happens when x is 3. So that means that's something that's going to cause my graph to be discontinuous at that x value. I have to figure out what the coordinating y value is for that. To figure out what y is, remember we're going to substitute my x value into the linear function here. Gets back 6. So this is my removable discontinuity. At 3, 6, I'm going to have a hole or removable discontinuity in my graph. So we're going to count out 1, 2, 3, and up 6. And draw an open circle to denote that my line is discontinuous at that particular point. Then you graph your line as normal. Connect our dots, right? Make sure that you're not drawing a line through the hole we just created. All right, so on problem number 3, this time the top is not factorable, but the bottom is. So we're going to rewrite this as 2x squared on top, and on bottom we're going to factor it to x minus 3, x plus 3. We check to see if there are any factors that are common to the top and bottom. In this example, we don't. So this one is not going to end up to be a linear. It still looks like a rational function. So what we're going to do is switch gears to our RATEY method that we learned earlier this week. So first we're going to cover r's, the roots. This happens when we set the top equal to 0. So 2x squared is equal to 0 when x is 0. So that gives back a coordinate of 0, 0. Asymptotes are found. Vertical asymptotes is found when we are setting the bottom equal to 0. It's already in factored form for us, so we set each quantity to 0. So I have a vertical asymptote at x equals 3 and x equals negative 3. The next part of our RATEY method is our T's, right, for R and A. So remember, this is checking to see if my root is tangent. You'll know if your root is tangent if one of the factors is squared. So I do have a squared factor, which means that this root is tangent. And remember, again, tangent means bounce. So you'll be bouncing off the x-axis at 0, 0. So I'm going to plot my point 0, 0, and I'm going to write up there a little b to remind myself at that point I need to create a bounce. All right, the second T is under asymptote because it's asking if any of the bottom factors are squared, which it's not. So what this tells me is the behavior of the graph around the asymptotes. So remember, it can either be coming in towards the asymptote on either side of the asymptote in the same direction or in opposite direction. So this one, since it's not a squared factor on bottom, and we do have to check both factors because we had two of them, right? So we have two asymptotes we have to check. Since neither one of them is a squared factor term, that means we are not together. We're going to be opposite arrows for a graph on either side of my vertical asymptote. Next is E, which stands for end behavior. End behavior is found by taking the first terms and writing them as a ratio. So we have 2x squared over x squared. All fractions should be simplified if possible. So I have y equals 2. So this is my end behavior. At the very ends of my graph will be approaching the line y equals 2. So we draw dotted lines on the extreme left and the extreme right. And then we also put out our equation for the asymptote there. And y is the y-intercept. The y-intercept is found when I substitute in 0 for all my x's. So if I plug in 0 on top, right, and 0 on bottom, I get back 0. We already have that point. I still have not done my asymptotes. We forgot to do that. So over here on 3 and -3, we've got our asymptotes that are vertical. Don't forget to label them, please. And if you like to highlight them to remind yourself that we cannot cross vertical asymptotes, you can do that. All right, so now we have all the pieces that we need to try to fit this graph together. I want to remember about the bounce here. To me, that's where I want to go first. Since I have to be bouncing here, I'm either going to be an up bounce or a down bounce, right? We have this horizontal asymptote here, so this is going to be facing downward, like that. On our vertical asymptotes, remember, these are both listed as not, so that means they have opposite arrows on either side of the vertical asymptote. So if this arrow is down, that means on the other side of the asymptote, I must have an up arrow. Okay, same thing with this vertical asymptote. Since this has a down arrow, when I move to the other side of the vertical asymptote, it must be an up arrow. Okay, remember your asymptotes are kind of like magnets and they're pulling the graph at a curve towards them. So that must mean these pieces look like this. All right, so on example 4, remember we're always going to check to see if there's anything that we can factor. And I notice at the bottom can factor into x minus 4, x plus 3. And then we need to check to see if this can be further simplified, and this is an example where it cannot. So we're going to move into the RATEY method then. So we have R for roots. This is when I set the top equal to 0, but -1 cannot be 0, so that means we have no roots. It will not be touching the x-axis. So we're moving on to the letter A for asymptotes. This is when I set the bottom equal to 0, and it's already in factored form for me. So what we're going to do is set each factor equal to 0. So I have vertical asymptotes at x equals 4 and x equals -3. So over at 4, we're going to draw our vertical asymptote. Make sure we label it with the equation. And if you like to highlight to remind yourself that these are asymptotes that we cannot touch, The next letter is T. Remember, we're checking to see if the root is a tangent bounce, and I don't have any roots. This T is checking to see the behavior of the graph around each asymptote. So we need to look at each factor and check for if the factor is squared. We don't have that, so that means on each one of these vertical asymptotes, we have opposite behaviors. They're not together. The next letter is E. E is for end behavior. End behavior is by taking your ratio of your first terms. So we have y equals -1 over x squared. All right, you simplify this if you can. This one doesn't, so then we have to analyze it if it's top, bottom, or balanced. And this is bottom heavy. And on our yellow chart, remember, from the parent function of 1 over x squared, we can determine the end behavior arrows. Since this one is the squared function, right, the end behavior arrows have to be the same, and since we have a negative sign, it means both of the arrows are going to be on the underside of the x-axis. The last letter in RATEY is y for y-intercept. This is when you're substituting in 0 for your x's. So 0 minus 0 minus 12. And we have a -1 on top, so this simplifies to 112. And we get to graph that slightly above, like so. All right, so we have all the pieces of the puzzle that we need here. And now it's just a matter of connecting them so that they make sense with all that we have. So what we're going to do is, I know that I have to go through this point, but I do have end behavior asymptote here. So that must mean my graph looks like this. And some of you guys might be going, wait, that looks like a bounce. But remember, bounces are only called bounces if we're touching the x-axis, right? This is not that. It's just a local min for a graph instead, okay, or a turning point. So we have the knots here. So I have an up arrow here, means I have to have a down arrow here. And the same thing for this one, because we are not together. So that these arrows are going to have to connect in this fashion.